In the first part of this video lecture, we have reviewed the algebra of left open, right closed intervals. We have also reviewed the concept of pre-measure, and then we have defined a pre-measure on this algebra that would correspond to the Lebesgue measure. We have also reviewed the Carathéodory extension theorem, and then finally combined the fact that this is a pre-measure whose proof we have omitted, plus the Carathéodory extension theorem whose proof we have also omitted. We have combined them to show existence of the Lebesgue measure. And this second part of the lecture, we're going to follow the same pattern, so we omit all this revision and show how the same procedure allows us to define Lebesgue Stieltjes measures and relate them to distribution functions. So let us move straight to the discussion of what Lebesgue Stieltjes measures are and distribution functions. And Lebesgue Stieltjes measures are the following. We have a function f, whatever function given to us, denoted capital F, from the real line to the real line. So finite here, we're not talking about extended real numbers. This is a function that assigns finite numbers to finite numbers, which is continuous from the right and non-decreasing. We are familiar with those types of functions, aren't we? These are exactly what distribution functions are for random variables, but let's keep this for a later moment. So functions which are right continuous, non-decreasing. Then the theorem says there is a unique measure that we denote by m sub-index f. The sub-index here to indicate that this measure depends on f. It was created using f. On the sample space, the real line with sigma algebra, the Borel sets, there is a unique measure that assigns to each left open, right closed interval exactly the variation of this function f on that interval. So as in the first part of this video lecture, we're not going to reproduce all that process. Again, the process to justify existence and uniqueness of a certain measure is through a pre-measure. We have to specify the pre-measure and afterwards prove that it is indeed a pre-measure. And of course, we're going to consider again the algebra of disjoint unions of left open, right closed intervals on the real line. And we're going to define first the measure, by definition, the measure of a left open, right closed interval. We take it as the variation of the function capital F on that interval. We take, if the left end of the interval is minus infinity, we compute it through a limit. If the right end of this interval is plus infinity, we also compute it through a limit. You can see the details in the lecture notes. And then for any set which is not exactly of this form, but is the disjoint union of intervals of this form, we define the measure of that set to be the sum of those finitely many left open, right closed sets. Again, I should emphasize this definition does not depend on how we write A, how we express A as a finite disjoint union of intervals. There is more than one way to do that. There is a small, simple example in the lecture notes. Anyway, whenever A can be written as disjoint union of left open, right closed intervals, we define the measure of A to be this, and then afterwards we prove that this indeed defines a pre-measure. We'll omit the proof of this fact. And as in the first part of this video lecture, just having a pre-measure is enough to guarantee by Carathéodory extension theorem that there will be a unique measure defined on the sigma algebra generated by these intervals, which is the Borel sigma algebra. There is a unique measure satisfying this for intervals of this form. We conclude this video lecture with two remarks. First, if we take the function capital F to be the identity function, it just says f of x equal x, then the Lebesgue Stieltjes measure, mf, corresponding to this function, is simply the Lebesgue measure on R. And the second remark is the following. Let us first introduce another definition, which is if the function f is not only right continuous and non-decreasing, but it also satisfies these two properties. It is 0 at minus infinity and 1 at plus infinity, then we call it a distribution function. Then what the previous theorem says is that this will be a measure. There is a unique measure on the real line which has assigns to each interval the variation of f, and so it will be a probability measure on R, because we can compute the measure of R by taking limits exactly when we send the left edge of an interval to minus infinity and the right edge of an interval to plus infinity, so it will assign measure 1 to the entire sample space, the entire sample space being R here in this case. And more interestingly is if P is a probability measure on R, then we can define f of x to be the probability of all points of the real line. I'm denoting them here by little omega, but I could have been using also x because these are just numbers. So we define the function f, this is a definition, we define the function f to be the probability that our point lies to the right of a point B. So this is f of b, not f of x. Then this is a distribution function, and the Lebesgue Stieltjes measure corresponding to this distribution function is p. So in fact, these two objects are equivalent. Which objects? Probability measures on R and distribution functions. These two objects are equivalent. You can define a unique probability measure from a distribution function. You can define a distribution function, unique distribution function from a probability measure, and this operation is reversible. If you do this, you get again the same probability measure, and if you do this, you get again the same distribution function.